continue talking about the quality control. Let's go straight to slides. So there is an important principle called the principles of variation, that any process will generate dimensions that's basically randomly distributed. So that's why you notice, like, sometimes they say, or if you look at the 2D drawings of parts, you will usually find dimensions like this, like say 5 plus minus, let's say 0.1. So these tolerances here represent the required variation, or the designer acceptable variation, that the part will still work. And it's very important here to mention that non-manufacturing processes, conventional or non-conventional, they have some source of variation, and these sources can be the vibration in the system, the guideways errors, the perpendicularity between guideway and spindle axis, or many sources that can generate variation between part and another. So if you take the part, the cylinder coming from let's say external turning process, you expect it not to have really this perfect kind of cylindrical shape, and when you measure the diameter many times along the center line, you will find the diameter here is not exactly as the diameter here is not. It's never. There is some variation between each intersection, each section and the next one. And also, if you get all these measurements and got the average, so you will find, let's say the diameter is 5.22, for example, as an average. If you make another piece, you will find that it's a different number. Like the average may be 5.08. Like if you measure many sections and got the average, for example, you will find surprised that the diameter is different from the other one. So because we know that there is many sources of variations in the manufacturing process, we expect there is some variation to happen, and this is very well known. That's why the designer will give you the dimension already with the tolerances that shows the acceptable variation for the designer. To represent the variation, we talk mainly about many parameters, but there is the average or the mean that represent the central value of the dimension measured, and the variation represented by the standard deviation. So for example, like if you look here, this represents a diameter like maybe 100 pieces of the part you got as a sample, and you measure the diameter, and you plotted the diameter on the horizontal and the count or the frequency on the vertical as a fraction of the 100. So you will end up finding the distribution is like this bell shape, or the normal distribution. So it's really very common to find yourself in that situation, and the mean or the central value on this shape, for example, here is 9.95. The variation can be represented by the standard deviation, so which basically represent this variation here, like on along the diameter axis. So like you can represent also the variation by range, which is a difference between the maximum and the minimum value, which is 10 minus 9.9, right? But the commonly used representation of variation is the standard deviation, which will show here that we have actually mathematical formulas you can use. So for the average, you just add the values together that you measured and divide by the number of pieces. And for the standard deviation, you use this equation, which is sigma xi minus x bar, which is basically what you calculate here is x bar. So every single measurements that you made minus x bar square divided by n minus 1 and then the square root. So it's very important to be familiar with the average and the standard deviation. We'll explain them more later in examples, but the variation concept or the variation principle is very, very important to understand from the beginning, because you will find this in all quality control problems. So the basic forms of variation, there is assignable and there is common. Assignable means it's caused by a factor that can be identified and possibly managed. Like for example, a poorly trained employee that creates a variation in the finished product output. So if you have untrained operator in this machine, and he's supposed to do certain procedure in the manufacturing process, his training and his cleverness as an operator of this system will affect the dimension that you get at the end. But there is common variations which is inherent with the production process. So to understand the difference more, like let's say you have some product that include, you will make a hole, like let's say a hole like this in a drilling machine, something very simple, and the hole has specific diameter, let's say phi supposed to be 7 or 8 millimeter. So how this 8 millimeter happens is you will have the operator put the drilling tip here, drilling bit here, and here is the part like that, and then supposed to rotate here but certain speed and then make the feed in this way, so you will go here and cut the diameter you want, right? So very simple process. So the sources of variation that's kind of assignable is, let's say the operator, instead of putting the right tool material, it was supposed to be carbon steel or some sort of a grade of steel, he bought a different tool. That specific operator used a wrong tool material, or instead of securing the tool exactly as it's supposed to be in the machine tool or in the chuck here in this example, he actually did not do the tightening or the clamping correctly. So now the tool has some sort of vibration or wobbling or something while. So this all is just from the operator. He has less training, or he has a problem in his skills that make him do these problems. But this can be fixed by simply train the operator, right? Just train the operator and make sure he knows how to do his job. That's it. But there are common variations or inherent variations, sources of variations, which is basically is by default happen for this process because that's how it works. Like for example, you have here certain motor, right, and certain driving mechanism or gearbox or some mechanism in between the tool and the workpiece. So there is vibration, right? So this vibration will cause a variation in the diameter that we are reducing. There is wear going on, like you put the tool and you are now cutting metal and metal. There is some wear going on in the tool. There is also the material, this material specifications, the part material specifications. It also affect how the result will look like. The same for the material of the tool. The whole system may be inside a workshop that the temperature varies between, let's say, 75 degrees Fahrenheit and 85, let's say. So if the temperature is varying like this will affect all these metal parts, so there is a variation. So all of these are inherent, these are common, that will happen because this process cut the part in this way. So because of the concept of the cutting process itself. So these can be improved, but they cannot be eliminated. So can be improved by basically if I get a smoother motor instead of the one that makes all this noise or vibration. The same for the gearbox. If I get a new gearbox or something will help to reduce the vibration. If I made sure that the tool material and tolerances on the tool are, really high grade, that I can depend on, all these kind of things can really, if I control the temperature, so these can be improved, but again they can't be eliminated. You can't really eliminate the motor or the gearbox or the tool or the part. I mean, now you eliminated the process. So again, the assignable causes of variation or the assignable variation, these are variation that can be fixed or even eliminated because they are not inherited with this process. It's because of something that's not normally inherited with this process. Like, normally when you have a process, you have a trained operator to work with it. But if you, for some reason, the operator that work in this machine didn't show up this day, and you have to put someone else who is not well trained to deal with this system, that's all of this is assignable variation that can be eliminated or at least fixed. But for the common variation, these are actually a part of the process. That's how the process work, that cannot be eliminated but can be improved if you want to improve the results of this product. If we talk about cost, I mean, if you talk about history a little bit, there is a famous guy in the quality world called Tagushi. So he was saying, we are trying to reach upper and lower specifications. There is target value. So the traditional thing, like if I'm talking about a diameter of 5 plus minus 0.1, so the 5 will be here, and here 5.1, and here 4.9, right? So the traditional view was, okay, if I'm within these, I'm okay. If I'm within these limits, I'm okay. If I'm go out here or here, I mean higher than this or higher than this, then I will pay more for cost. But for Tagushi, he's saying if you, as much as you go from the mean value or the average value, then you start to have increase in the cost. All right, so we'll stop right here and we'll continue next time. Thank you so much for watching.